All right, let's do another example, and this time we'll design a column. We're going to select a W18 and use a 992 steel. That's the commonly used material. We also have our design loads here that we can calculate the ultimate axial force required of the column. Right here we have the boundary conditions. We see a pin and we see fixed. And remember, these are, when we draw these things like this, it's idealized, and we don't want to use the theoretical value of K. We want to use the design value of K. These are ideal conditions. Those don't exist in the real world. We actually do have some flexibility in something like, in some kind of a rigid connection like that. So we need to use a slightly higher value of K. And so you see in table C, in table C, A7, 1, right, that the design value is 0.8 and the theoretical value is 0.7. So we use a slightly longer effective length in design. Right, this effective length here, KL. Okay, so we can hold this in our mind for a minute, and now let's go and start the design problem. So we know from design that we need P sub u to be less than or equal to the factored nominal strength. Right, this is the factored, that's this part, factor, right? The factored nominal axial strength or resistance. I'm going to call it resistance. Or also you can sometimes call it strength. Okay, so next thing we need to do is calculate the demand. So we know that since we have dead load and we have live load, we need to do 1.2, sorry, let me back that up. We need to do P sub u is equal to the maximum of 1.2 dead, and sorry, not 1.2 dead, 1.4 dead, and 1.2 dead plus 1.6 live. So we have 140 kips and we have 600 kips. If you plug those in, you'll find that that's the case. So this is our PU. This is our ultimate load. So when we plug back in here, we've got 600 kips less than or equal to phi Pn. And this phi Pn, remember now, this is the minimum of all of our limit states. Right, and for our limit states, we had flexural buckling and we had local buckling. Okay, now for design, we don't really want to mess around with this one. For one, if we're picking a column, right, we're going to go back to this chart so many times, you're going to be so tired of it. But when we go back to here, if you remember, or if you don't remember, you should go back and look at the notes, that this curve describes flexural buckling, and then local buckling only came into play when we had higher flexural buckling stress. And so this decrease was kind of the local buckling effect, right? This is the effect of local buckling if we compare them all kind of in one graph, right? If we compare them all of them being like flexural buckling and local buckling, if we compare the two different limit states in one graph, we see them here. Local buckling typically will only come into play when we're in the inelastic zone, right? The inelastic flexural buckling zone. Okay, so what does all that have to do with design? Well, since we know this state is a lower, right, buckling stress, it's a lower buckling load, we don't necessarily want that to happen, and we don't really want that to happen in our columns. Okay, so we're that's one reason we're not going to consider it. Another reason is to not consider it is that, well, this is a complicated one to do. There's a lot of different variables in there. The calculations are more complicated. Another reason is that W sections, for typical column sections, W sections don't tend to have slender elements. Right? So you remember the elements are the rectangular rectangular portions of the cross section. So that's one element, that's another one, here's one, and here's one, and here's the last one, right? The web. So we've got all these different elements, and typically W sections don't have this for compression, right? For compression. I'm going to erase all this, so just describing what we're doing here. So, okay, what does that have to do with the design? Well, since this is the case, since we know it's the lower stress, and since it's also very complicated, relative to flexural buckling, we typically do not consider local buckling for the design. So I'm going to go ahead and take all of this away. So for design, we really want to focus on flexural buckling for the most part, right? So since this is the case, again, I'm going to, I'll leave this one here. How about that? We'll say, okay, now I know. How about we put it here? And this will remind you of that discussion. Now I know it's 0.9 F critical AG. Trouble is, both of these are dependent on the cross-section. Right? F critical is a function of KL over R. And of course AG, well, that is the cross-section, right? Cross-section. So KL over R, well, the K and the L, this part is taken care of, that's good. But for R, we don't know R, right? This is cross-section dependent. Well, we don't have it because we don't have a shape. We don't have the shape. Okay. So now you see the problem here. What do? What are our choices? Well, we don't really have very many choices. So what we do in this case is we guess. So let's guess an F critical. So I'll say F critical 1 is equal to, let's just say 2/3 of Fy. This is a good starting point. You could really pick anything, right? But 2/3 of 50 KSI. You could pick anything, but 2/3 seems to be a pretty good place to start for normal size columns. So since I have this now, I can go and rearrange my equation to say 0.9 and 33 KSI. And now that gives me a target, AG required. Right, so from that, let me bump this over a little bit so we can just put it all in one line. This should be equal to 20.2 inches square. Now I have a target. Whoops. Target. There we go. We have a target, so I'm going to go with here and I'm going to try. I'm going to go into the dimensions section and I'm going to pick a W18. Right, a W18 by 71. Looks like it'll work because AG is equal to 20.9 inches square. I got really close to this number, 20.2. Okay, great. The next thing I need to check is something that I haven't looked at yet too much in our notes, but I need to check the R minimum. And the R minimum is given by section E2 in the user note, And it says that LC over R should probably be less than 200. And this makes a lot of sense if you, again, think about this curve. This curve is like this. For Fy equal to 50, our 4.71 square root e over Fy value is about 113. So remember that this axis is LC over R, which is KL over R, right? So my slenderness ratio, this is kind of saying that the maximum slenderness ratio is 200, right? That's the maximum. Well, look where that lies. That's almost double. That's almost double this value. So I'm way over here. So why is it saying this is a user note, right? Keep in mind that user notes, they're not a requirement by the specification. They're more of just kind of a tip, right? They're sort of a tip. Or telling us something that's sort of by convention. Well, this is a pretty good convention to follow, because if I look out here, what do I notice about the buckling stress? It's super low, very low buckling stress. Right? That doesn't make a very good column. So if I exceed slenderness of 200, I mean, I'm allowed to do it, but it doesn't make a very good column because the buckling stress is so low. All right, so let's get rid of this just to explain why. Well, you told me about LC over R maximum. So how does that translate to R minimum? Well, I just rearrange this, right? So that means the minimum R. So if I make this smaller, that means the ratio gets bigger. So I can just rearrange and say R minimum is equal to LC over 200. And so I have, what do I have? Oh, I have KL over 200. Now I need to apply my K. I'm going to do some scooting here so I have some room. Oops. That makes this 26 feet divided by 200. And I need this to be in inches, right? So I better multiply that by 12. Multiply that by 12, and that gives me R minimum over here on the left equal to, what do we have? 26 times 12 divided by 200 is 1.56 inches. Okay, so remember, I'm trying this 18 by 71. Ry is the minimum from 18 by 71, and that value is 1.7. So we're good. That part's okay. This gross area is okay because it's bigger than AG required. Okay. So, does that mean I'm good? I can just go ahead and pick this one? No. Right. Now I need to check the F critical of the W1871 with a length of 26 feet. Because remember, I just guessed F critical. I don't actually know that this thing has an F critical, what I exactly the same value that I guessed, right? I just guessed 33 KSI. That gave me a target that led me to this, but now I need to close the loop, right? I need to confirm my assumptions. So I can do KL over RY gives me a 183.5. This is lower than 200. I already knew that because I checked this, right? But it's just nice to show that. Lower than 200. And it's also greater than 4.71 square root e over Fy. This is 113 for Fy 50. That means I'm going to E3B, right? So my F critical is equal to 0.877 F Euler, and that's 0.877 times pi squared Young's modulus over 183.5 square. And that gives me 7.45 KSI. This is not equal to the F critical that I assumed, 33 KSI. Right? So that's a bad sign. But even still, we can go and just check, right? We can, even though this is clearly not going to work, what we should do is go ahead and just, if these were close, we might get lucky and find that VPN works. But let's just check. We already, it's pretty clear that this is not going to work, but in practice, we should probably just go ahead and check it. So we've got 7.45, because we might be close, and it might actually work. 20.9, so 7.45 times 20.9 times 0.9 is 140 kips, 140.1 kips, and that is no good for a PU of 600. Okay, so let's go and try the next one. So what do? Well, we said the last time that F critical was 33 KSI, and we found out from over here that when we did that, right, we got 20 inches square, and then we ended up with something that had a much lower buckling stress. So what I should do is I should pick something between, and then I got an F critical equal to like 7.5, right? KSI. Oh, we'll make it 7.45 KSI. So next guess, I'm going to go in between these two. Let's split the difference. That's about 20 KSI, right? Split the difference between these two. All right, so if I go through the whole thing again, now I go back and say 600 divided by 0.9, 20 KSI, and I get a required area of 33.3 inches square. That's my AG required. Now I'm going to try W18 by 119, because AG is equal to 35. Clean that up a little bit. And RY is equal to 2.69. I have KL. I'm going to scoot this over. Let's go ahead and make this over here. So that means my KL, let's just keep scooting. Try to use the same format. So I know that KL over RY is equal to 26 feet times 12 over 2.69. And that gives me a ratio of 116, which is less than 200. It's also just slightly over the 113, right? This was, 4.71. This is my, the limiting slenderness ratio from E3, square root E over Fy. So I need, therefore, based on this, I need E3B. That's the elastic zone, right? This is the conceptual part, elastic zone. Okay, so I get the same from E3B. I get the same relationship, 877 F Euler. I have 0.877 pi square Young's modulus over 116 square, right? That's my KL over R. Squared. And that gives me, let's just find out. Make sure I have the right thing written down. 0.877 times over 116 square. I should have 18.65 KSI. Ooh, look, I'm much closer on this iteration. 18, almost 19 versus 20. Good, this is a good sign. Also, my areas were very close as well. So it's looking good. Next thing I need to do, right, I'm saying this is pretty close to my F critical 2. This is assumed, so I'm happy. And lastly, I just want to go ahead and make sure that it works. 0.9 times F critical, that's 18.65 KSI, times area gross was 35.1 inch square. And I have 1865. I have 589.2. Oh, just not quite enough. Whoops. 600 kips. Still no good. Okay, now what? Well, I can do one more iteration, or since I'm so close, I can just go one size up. I'm so close, right? So close. That's not a very good G there. Go one size up. So from a W18 by 119, I'm going to go one size up to a W18 by 130. AG is equal to 38.3. My KL over RY is equal to 115.6. That's greater than 113. That's my 4.71 square root E over FY. That means I'm in E3B still. F critical is equal to 0.877 times pi square E over 115.6 squared. And I should get 18.79 KSI, arriving finally at 0.9, 18.79 inch square, or sorry, not inch square, KSI, and 35.1 inch, no, sorry, this one, right? 38.3 inch square. I get 648 kips, which is greater than PU. I'm happy. Okay. And I don't have enough room on the bottom here, but typically I would write it down here on the bottom, and then I would write use W18 by 130, and I would box it, maybe even a double box, and I would say that that's good. So I'm done. 18 by 130 works, and you saw the iterative method for solving the design of a column, particularly when you have some weird shape like this for a column, which is W18, and we'll talk about that in the next example. All right.